All right, here is the study guide key. So these first chunk right here, know the names, formulas, and charges of. I can't really teach you that anymore. You just need to memorize those. I've given you a couple charts of those. So Google them if you need to, do whatever you need to do. So for the second part here, calcium chloride is combined with silver nitrate, and we want to know the mass of silver chloride that forms. So first things first, we should write our formula out here. Write our equation. So I tell you two of the reactants and I tell you one of the products. You should be able to come to this on your own by just switching the positives. But if you can't, you should be able to deduce what would obviously be left. And then you need to balance this. So we would just do this and this. All right. So if you have 15 grams of calcium chloride, first thing you need to do is turn that into moles, which again you should be pretty solid at this point. And if you do, you'll get 0.135 moles of calcium chloride. So now let's do the same thing for silver nitrate. You have 45 grams of silver nitrate, and that will give you 0.265 moles of silver nitrate. And the question is, how much silver chloride will you form? So this is obviously a limiting reactant stoichiometry problem. So what we need to do is turn these both into moles of AgCl, and whichever is smallest is the correct answer. So there are 2 AgCl for every 1 CaCl2. So that's just twice that, which is 0.270 moles AgCl. And then we do the same thing over here. 2 AgCl for every 2 AgNO3, and that is 0.265 moles of AgCl. So then which one is the correct one? The smallest one. So last step, you just turn your moles of product into grams of product, times in a line, 1 mole on the bottom. The whole thing weighs 143.3, and so that'll give you about 38.0 grams. Awesome. So for the next part here, this is just MC delta T. So this is just your Q equals your mass times your specific heat times your change in temperature. So your mass is 150. Your specific heat for water is always 4.18. Your change in temperature is 80. This is a part that people mess up a lot. The change in temperature is 80. And so you do that and you'll get about 50,160. All right, I'm actually going to do 5 first. 5 is easier than 4. I put them in the wrong order. So this is MC delta T equals MC delta T, meaning you're taking something hot and putting it in something cold. So if Q equals MC delta T, then the Q, the energy that the hot metal loses, is equal to the energy that the cool water gains. So this is just the MC delta T of your metal equals the MC delta T of your water. So of your metal, you have 8 grams. You don't know the specific heat, that's what it's asking for. And your change in temperature, you went from 100 to 20.1. So your delta T for your metal is 79.9. Your water, you have 150 grams of it. The specific heat is always 4.18 for water. And your delta T, you went from 19 to 20.1. So your delta T is 1.1. So you solve for that and get about 1.08. Beautiful. So now number 4 is exactly the same thing. Just a couple issues. I forgot to give you the mass of copper, so we'll just say 50 grams because why not? So it's the same issue. It's still MC delta T equals MC delta T, but you need to break your delta T down. So for your metal is Your delta T is the initial temperature minus the final temperature, because your initial is going to be your hottest and you want a positive number, so you want a big number minus a small number. Whereas your water is going to be like this, because your final temperature is your bigger temperature because it's heating up. So we take this and we just substitute in all the terms. So I said we have 50 grams of copper. Copper's specific heat is 0.39. And now we have 250 minus final temperature equals the same thing, same information for water. 300, 4.18, TF minus 21. And these are degrees. And so now you just do the algebra, right? You do some math, you'll get 4875 minus 19.5 TF equals 1254 TF minus 26334. So then you just combine like terms and solve for a final temperature of 24.5 degrees Celsius. All right, so now number 6 just happens to work. Not a great practice problem, but kind of, so you can just realize, it helps you practice realizing when something just works. If you look at this, we want strontium on the left, we have it on the left. We want graphite on the left, we have it on the left. We need 3 halves, which is 1.5 O2. We have 1 plus a half, which is, 1.5 O2 is 3 halves. Right, so we have 1.5 O2s. And then we want some strontium carbonate on the right, which we have. We don't want strontium oxide, but there's 1 on the left and 1 on the right, so they cancel. We don't want carbon dioxide, but there's 1 on the left and 1 on the right, so they cancel. So this works. This just happens to work. Which the next one most certainly will not. And then you just sum those and you get negative 1220 kilojoules. All right, so this next one is not as easy, which is good practice. So you look at this and we need FeO on the left. It's currently only on the right, so we need to flip this bottom equation. So everything that was on the right goes on the left, everything that was on the left goes on the right, and this becomes negative. Beautiful. Next, I see that we need FeO, we have that. So we need, we don't need any Fe3O4s. And if you look, your Fe3O4s need to cancel out. And right now they can't for a couple reasons. One, because they're both on the same side, so they'll add. And two, there's 2 of these and 1 of these. So we need to flip this around so this and this can cancel. And it's also good to flip this around so then this and this can cancel. So let's flip this top equation. So it's going to become 2 Fe3O4 plus CO2 yields 3 Fe2O3 plus CO, and then this becomes positive. All right, we're almost done. So now our last problem here, we have 2 problems left. These need to cancel, and they don't. So we need to double the bottom one. So this becomes a 6, this becomes a 2, this becomes a 2, this becomes a 2. And so now this is times 2. And then lastly, if you look at this, we need our Fe2O3s to cancel right here, and they won't because you only have 1 here and 3 there. So this needs to be multiplied by 3. So now you have 3, 9, 6, and 9. And then again, multiply this by 3. So now, if we sum this, our 2 Fe3O4s cancel. Our 3 Two O3s cancel. We have 2 CO2s and 1 CO2, so we have a total of 3 CO2s on the left and 9 over here. So these 3 cancel and leave you with 6 over here. The 3 take away from the 9 is 6. And then again, we have 3 COs on this side and 9 COs on that side. So the same thing happens. Those 3 turn this into 6. So now if you sum this, I know it's not looking exactly like we want, but it's pretty close. If we sum this, you get 6 FeOs from right there, plus 6 COs from right there, yield 6 iron, plus 6 CO2, and this sums to negative 66. So now, if you look at this, this is just exactly 6 times the answer. So what you need to do is just divide everything by 6. So your final answer is negative 11. That one was a little trickier, but doable. All right, number 7, you guys should be pretty good on these, so I'm just going to do a couple. Oxygen, remember oxygen has 8 electrons, so it all better add. So for the electron configuration, 1s2, 2s2, 2p4, and again, 2 plus 2 plus 4 is 8, so that works. And then if we want to do the orbital diagram, 1 up, 1 down, 1 up, 1 down, 1 up, 1 up, 1 up, and then we have to go back down for that 4th one. So there you go. Beryllium, 1s2, 2s2, which is good because beryllium has 4 electrons, so that works. And then 1 up, 1 down, 1 up, 1 down. Awesome. So for 8, basically the most reactive are the ones that are on the ends. They're on the sides, the left or the right. And the smallest is further up and to the right. So furthest up and to the right here is fluorine. So fluorine is the smallest. And then closest to an edge, or if they're all in the same spot, closest to the either upper right edge or lower left edge, is fluorine. So fluorine gets the circle and the square. All right. Number 9, de Broglie wavelength. If you recall, the equation for the de Broglie wavelength is Planck's constant divided by mass times velocity. So it tells you the wavelength. So 6.0 times 10 to the 7th. Planck's constant is a constant, hence it being called Planck's constant. You could Google it, you could look in our previous homework or whatever you needed to do. I wouldn't expect you to memorize that. The mass is what you're looking for, and the velocity is 3.0 times 10 to the 8th. That should look familiar to you. You go ahead and solve this, and you get a mass equal to 3.68 times 10 to the negative 50 kilograms. That is really, really, really tiny, but that makes sense because we're talking about a photon. All right. We didn't explicitly discuss this yet, and we will next class, but basically higher boiling point is from something being more polar. So if you look here, CO or NO, basically which two have a greater difference in electronegativities? NO does. All right, last problem, I'm just going to do A. So let's add up how many we get here. B gets 3, chlorine has 21, or 7 each, so 21 apiece. So that's a grand total of 24 electrons. Boron is both the least common and the least electronegative, so it goes in the middle. Your chlorines go around the outside. And because there's 24, I know that I need to have 8 on each chlorine, and then I'm out. 8 times 3 is 24. So I know right off the bat that I need to have a double bond, because I can't have 8 on each chlorine plus some extra on boron. It just won't work. So you can pick whichever one you want to put the double bond on. It doesn't make a difference, and that's it. Technically, resonance structure would be now putting the double bond there, now putting the double bond there, but it's close enough to me. I'm not really too concerned about that. So now you look at this, your central atom has 3 electron domains, none of which are non-bonding, meaning lone pairs. So this is going to be the same electronically and molecularly. This is trigonal planar.